You're welcome.
Okay, so
So let me welcome Fabrizio Ghezzi, from Pavia and the Radio School of Management in San Diego, right? And is discussing about a new class of Renyi-Type monitoring statistics. Thank you, Fabrizio.
Okay, thank you very much. So thanks for the acceptance of the paper, and also so I just wrote first junior virtual time series, so I hope many more will follow in the next years. And this is just joint work with Eduardo Rossi and Lorenzo Trapani, who might be here around. So this first slide is about what a paper is doing. Okay, so in the case you fall asleep after that, you don't lose anything. So what we do in this paper is really kind of simple. We take a linear regression model, very simple. And what we do is that we introduce a new class of monitoring statistics that allow us to detect changes in real time in beta t, so in the slope parameter of this regression model. Okay, so for this new class of statistics that we introduce, we developed the whole asymptotic theory. That means that we study both what happens under H0 as well as under H1. And then we study basically what is the impact of the dimension of the dimension of beta on this limiting theory. And as last kind of theoretical contribution, we also studied the asymptotic distribution of the stopping time. As you will see, this is very much related with the delay of detection delay of the procedure. Okay, so why do we do that? So we're not masochists. We do that because we will show that these statistics will have a smaller detection delay. Okay, so as a big remark, this would not be classical structural break statistics. This would be real-time statistics. And you will see in a while what that means. So here, just a brief motivation, if that is the case. So the first two are two academic papers that I quote, while the third is a very kind of recent article on the Financial Times. So all these three quotes, they kind of highlight the importance of being able to kind of assess structural instability. So now we live in a very dynamic present where changes happen all the day. And what is really important, especially for financial institutions, central banks, and so on, is being able to detect breaks, not like with a huge delay, but with as little delay as possible. So meaning that I'm not interested if I have, for example, an hedge fund detecting a break like in 1997, I'm interested in detecting a break 2 weeks ago, okay? And so this paper is really concerned about this type of methodology, so real-time structural breaks test, okay? But before then getting to that, I want to just make the setup and review a bit structural breaks testing in the classical framework, so that I make sure every one of us has the same understanding. So again, all the paper will be about this linear regression model. And we only make, here I'm not stating any precise assumption. I'm just saying that beta t will be d-dimensional, and then both xt and epsilon t, they can have time series dynamics. Okay, so they have general enough assumptions to accommodate time series dependence. Okay. So now if I'm going to give you a sample of length m, so let's say m is yesterday, so a data set up to yesterday, date of stock returns, for example, then for you it's very easy to test whether a break has occurred. What you do is that you go and check. So hypothesis testing 2, and there are various ways. There's chow test if you kind of guess the date of the break, Andrews soup test if you don't, Newblom, and so on. So all these type of tests, they can be used to test whether a break has occurred in the past, okay? So then if you do not detect any break, what you can do is that you go on and set up a model by, for example, taking the least squares estimate of beta over your whole sample. Okay, that's clear enough, I think. But what happens is that in most situations of interest, think just about what I said, like that I am giving you a set of stock returns up to yesterday. So today, after the closure of the stock market, you will get a new data point. The same will be tomorrow, then Monday, and so on. So in these situations, we record new data every day. And so if the true question that should be of interest is not like a break has occurred 10 years ago, but is, okay, given if I cannot detect breaks, so I have a stable sample, but I'm sequentially recording new data and I'm using my model to kind of trying to predict or making some inference on this new data. Is this my kind of historical model still capable of explaining today's data? Okay, so this question is exactly what we are taking up. Okay, and it's a question of real time. Sorry,
Fabrizio, very quick one. So
Yeah.
maybe I missed that. So do you allow for partial breaks also? I mean, some
you will see, like here I'm not touching our theory yet. You will see in a moment what hypothesis we do. We actually accommodate that in a kind of way, smooth varying parameters, because after sometimes smooth varying is accumulates and you can detect basically the break. Okay, is that clear?
I will see later.
Okay.
Thank
So
you.
okay, thanks. You may wonder that it is a very easy task to record, to kind of do this type of test, but just have a quick glimpse at equation tree. That is not the case. Okay, so that is a very simple case where a law of the iterated logarithm kicks in and basically drives you the probability of falsely reject a null hypothesis of no break basically equal to 1. Okay, so you will erroneously reject the null hypothesis even if you don't have breaks. Okay, so long story short, in the statistical literature, this is a well-established problem, but not so in econometrics. So the first 3 guys to take this to econometrics were James Chu, Maxwell Stinchcombe, and How White in a famous 1996 econometrica paper. And since then, some people have, so they laid down the general framework, and then a lot of people, especially Lajos Horvat, they kind of worked on this topic, but still we miss a complete satisfactory answer. Okay, so here are the hypotheses that we actually are interested in. Okay, so the first hypothesis is just kind of stating like that we're interested in study the stability of beta t over time. So meaning that after M, so after yesterday, we want to make sure that beta t is not changing, okay, as we record new data. The hypothesis of the alternative is just basically is ugly, but it's just saying that there exists a K star. This K star is the timing of the break where beta is changing. So with respect to the question, we do not allow smooth kind of, we don't have an alternative against smooth breaks, but it's just kind of level break. Okay, so beta 0 is changing at K star to beta 1. Okay, that's the type of alternative we are interested in.
I got it. Yeah, thank you.
Okay, thanks. In order to do kind of hypothesis testing, as always, it turns out we need some statistic. So we will make extensive use of this QMK. This QMK will be called detector or detecting statistics, and it's just the sum of square residuals. So this sum on the kind of newly recorded data with beta hat M is the beta estimated over the historical sample on which we assume that there have been no breaks. Okay. Okay, so the monitoring scheme is again, we take from Chu, Stinchcombe, and White, and it's defined as a stopping time, this tau M. What is this tau M? Will be some point in time, and will be what? So if you have your detector, this Q, and then you have a boundary function, okay? So the monitoring proceeds that every time you get a new data point, you update your detector, and then you check whether your detector is crossing this boundary GMK. So if the detector is crossing this GMK, what you do is that you kind of stop the monitoring procedure, you come back with tau M, tau will be K star probably, and that case, tau K star, will be kind of your estimated time of break, and so you will have kind of estimated that there has been a detection. If instead the detector is always below GMK, you never kind of stop the procedure. Okay, so the process is called in control. But for a reliable inference, what we have to do is that we have to make sure that the probability of kind of falsely detect a break under H0 is kind of less than alpha, while under H1 is 1. Okay, so these are just 7 and 8 generalization of size and power concept in classical testing, nothing more than that. Okay. So now here comes what we do. What we do is that if you look at the stopping time, this JMK, ceteris paribus, will be determining kind of the shape of the kind of rejection regions for the monitoring. So what we do will be that we consider these kind of heavily weighted functions that we call Renyi weights, Renyi functions, G eta. So where they are called heavily weighted because we put a heavy weight on eta, okay? So that means that intuitively, what we do is that the first part of G is kind of just making sure that convergence happens. Then if you look at this K over K plus M, this guy is less than 1. So that means that if you raise it to some power eta large, this guy will be very small and will kind of compress the rejection region of the monitoring, making easier, if you can stick control for alpha, of course, crossing it. So that would result in a lower detection delay, okay? And here comes our first result. I'm not stating any condition. What I want to just, they are kind of mild enough just to say. What I really want to show is that the beauty of this result is that it is allowing us to basically compute critical values for complete G, eta, in a way that we can kind of do exact inference in this monitoring setup. Okay, we have, of course, here comes the fact that we study how big can be beta to not harm our inference. And beta turns out that it cannot be high dimensional model, okay? Because the dimension of beta impacts the rate of convergence in the asymptotic theory. Okay, so this is basically stating the distribution under the null hypothesis. And this is amazing because it allows us to conduct inference. For an applied user, it will be extremely easy because he will have all the critical values. He will put that this critical value in the boundary functions and will be able to make inference. Okay, so it will be straightforward for someone who is applied. Then we study the asymptotic under the alternative hypothesis. And here we just make sure that we have power. I don't want to touch upon this condition. So this condition just make sure kind of that there's a break and how big can be the break. So these conditions. So under these we have power. And I state them, this is kind of understating because these are two different theorems in the paper. The second part of the theorem, so from here, is that we are able to see what the stopping time, this kind of degenerate distribution is. It's not possible to derive an exact distribution, so a convergence in it to a normal, for example, but we can still get convergence in probability to AM. So it will be kind of degenerate convergence. Okay, so one thing that I omitted is that this class of functions, they work extremely well when the break is expected to be close to the beginning of the monitoring. That, of course, is not the case in majority of the situations because you can't kind of make some assumption on where you expect the break because you are making some modification to H1. So what we came up with is that we came up with a modification of the procedure based on the kind of machine learning literature where we have this kind of idea of computing more statistics. So both heavy weight and mild weight statistics, and then looking at basically which is the minimum of the boundary region, so the easier to cross in a specific point in time, and then so we combine them in this way, and this will be called veto, majority voting rule statistic. Okay, so then we make sure that we don't run into data snooping problem by exactly studying the distribution of this animal right here. So that will be kind of is a second part of the paper. I'm not touching because it has nothing to do with Renyi-Type statistics, so it is using them, but it's not kind of Renyi-Type itself. Okay, so this is just to say that we have this type of extension. I want to touch on simulation because I don't think I have time, but I want to just kind of recap on what we did. Okay, so we introduced a new class of monitoring statistics.
You have 5 minutes, huh, Fabrizio?
I have 5 minutes.
We were a little bit late. Yeah, we were a little bit late. So you have up to 5 after. Yeah, sorry.
So then I may kind of switch. Did you see the switch to the PDF?
Yes, we do.
Okay, so I'm just taking few tables to 2 tables, basically, very kind of straightforward to see, to show you what happens. So this is kind of the sides, the table of the sides of the monitoring. So this will be the eta. So the higher the eta, the smaller the boundary function. And these are different choices of M, historical sample. So what you can see is that kind of we control the sites. So this is very important when you have this type of monitoring procedure to kind of exactly because you have a sequential test. So the sites is only expected to grow over time. And as you can see, we always, so this will be empirical site, the kind of nominal sites is 5%. So it's always under control. It's just like slightly over sites in this case of 80.5 and 1, but is overall doing a pretty good job. Okay, and then here comes the distribution. This is under the alternative is the detection delay. So here I'm making a direct comparison with so-called kind of mild statistics, and these instead are the Renyi statistics. Okay, so as you can see, the detection delay. So these are summary statistics of the detection delay. As you can see for the Renyi case statistics, these statistics, summary statistics are much lower. So for example, if you go and look at the best case of the third quantile of the mild statistics, that is 27. The best you can do with Renyi is 22. So that means that you reduce 5 observation. So that might not be very big improvement. So in this case, I'm also I'm not coming up with the best thing we can because I want to be fair. So this would be a breakpoint K star is 30. So that means that the break is not very close. If I would have simulate like K star equal 1, that will be kind of that Renyi will be absolutely kind of half of what these mild statistics do, but that's not kind of overselling is not what we want to do. We want to be honest about that, and kind of we think like 5 observation in the third quantile is quite good because you are kind of at least improving what you could have done. Okay, so and this is let me just go back to recap. Okay, so this is just a recap of the paper. What we did was to introduce a new class of monitoring statistics, then develop the whole asymptotic theory, study the impact of dimension of B and the asymptotic distribution of the stopping time. Why did we do that? Because we showed that the proposed statistics, they have a smaller detection delay. Okay, that's all. Thank you very much for your attention. And if you have any feedback right now or just later on via email to me or to my co-authors that you may know them better than me, that's very welcome. Okay, thank you.
Thank you very much, Fabrizio. Thank you for your interesting talk. Are there any questions or comments by the audience? We have a couple of minutes before, we move to the break. So if you have any questions or comments for Fabrizio? So
yeah, I have a small curiosity.
Go ahead,
Enzo. Yeah.
Hi, Fabrizio. Nice to see you again.
Yeah, nice to see you.
Nice presentation. Really interesting, and also really a nice topic. I think it is really, and also the presentation was super clear. So thanks a lot. I just have a curiosity about the DGP that you're assuming.
Mm-hmm.
So the epsilon.
Mm-hmm. Yes.
Could not. It is. I think it is really. I don't know. Maybe it is too difficult, but can it be also heteroscedastic with some sorts of heteroscedasticity?
So you mean unconditional heteroscedasticity or conditional?
Yeah, I don't know if there is the possibility also of conditional, because it seems really difficult here to allow for this.
Actually, we make some very mild assumptions that allow epsilon t to follow also Ghezzi-type processes. So it can be conditional heteroscedasticity. So if you want to deal with unconditional heteroscedasticity, Then what you may want to do is that you want to kind of do in a piecewise way. So Lorenzo has some work on that, kind of in the
I saw the
you can use some trick like that, but in this case, like unconditional heteroscedasticity is not accounted for. We can make some extension and make it work in that kind of tricky way, but conditional heteroscedasticity is accounted for. But also XT can actually have kind of guard type of innovations. I don't know if that will be useful, but
so it could be basically it could be a martingale difference also.
Yeah. So what we model them is kind of we model them. You want to go ahead, Lorenzo, please?
No, you go ahead.
No, basically we model them as that is called kind of L something Bernoulli shift, where this something will be the number of moment restrictions that you impose. And this is general enough to really nest a lot of models. So even nonlinear kind of time series dynamic models. So yeah, it's kind of just based on coupling and the rate of decay of the sequence from the couple one. So it's kind of very general. I will forward you the paper when can be circulated. So then you will have a look at that.
Yeah, thanks. Thanks a lot.
Yeah, thank you.
Thank you, guys. So let me do this. I am stopping the recording right now.